Now we're going to look at the exponential function. So we'll start off with a bit of background. What is an exponential function? Let's take a look at an example. Here we have a graph of the function y equals 2 to the power of x. We call this an exponential function because x, which is the input, appears as a power or appears as an exponent. So an exponential function is where your input is a power. So we have a base, in this case the base is 2 to some power, and that power is our input. So we can see from the graph here, if we take an input of 1, our output is 2. If we take an input of 2, our output is 4. And this should make sense if you think about it. If you have x equals 1, if you input 1, well then y will equal 2 to the power 1, which is 2. So that's why our y value is 2. Similarly, if we take our input to be 2, our output y will be 2 to the power of 2, which is 4. And you can see that right here. 2 to the power of, what about 2 to the power of 3? Well, we know that 2 to the power of 3 is 8. So this is a simple example of an exponential function, this particular one, y equals 2 to the power of x. So let's take a look at another example of an exponential function. Here we have the exponential function y equals 3 to the power of x. And if we have an input of 1, we know that 3 to the power of 1, that is 3. If you have an input of 2, 3 squared is 9, and so on. If you have an input of 3, 3 to the power of 3 is 27, and so on and so on and so on. So you can see the exponential function 3 to the power of x here. How about another example? Here we have an exponential function 10 to the power of x. So y is 10 to the power of x. So we can see that 10 to the power of 1 will come out right here at 10. 10 to the power of 1 is 10. That should make sense. What about 10 to the power of 2? 10 to the power of 2 we can see is 100. 10 to the power of 3 you can see is 1,000, and so on and so on. So exponential functions are fairly straightforward concept. Your input is just the power. The base number will be defined and your input will be the exponent or the power. Now, the one that we're most interested in for this video is a particular exponential function y equals e to the power of x. So my base that I'm interested in is the base e. We've looked at the base 2, we've looked at the base 3, we've looked at the base 10, but what I'm really interested in is this base e. So this number e is a mathematical constant roughly equals to 2.718281828, and it's a non-recurring decimal. It is an irrational number discovered by the Swiss mathematician Jacob Bernoulli in the 17th century when he was doing investigations on compound interest. And if I want to be more technical, the strict definition of the number e is the limit as n goes to infinity of 1 plus 1 over n to the power of n. Now, we don't need to worry about this definition right now. We just need to understand that the number e is a naturally occurring limit when we talk about continuous growth. Okay, so what about this function here, e to the power of x? Let's look at this in a little bit more detail. So, we're looking at this exponential function. The exponential function is used when a quantity grows or decays at a rate proportional to its current value. What this means is that if a value is bigger, it will grow faster. Or if the quantity is bigger, it will grow faster. Or if it's smaller, it will decay slower. A simple example is to think of population. If you have a population of 1 million versus a population of 100 million, the population of 100 million will be growing faster than the population of 1 million because if there's a population of 100 million, there is more people around to reproduce, therefore that population is going to grow faster. So it's a natural idea. The exponential function is used when a quantity grows or decays at a rate proportional to its current value. We can use this function for many situations, including growth of bacteria or any population, radiocarbon dating, i.e. telling us how old fossils are, depreciation, or continuously compounding interest. And we've already looked at this. The basic example of the exponential function is written as y equals e to the power of x. So let's look at some properties of this exponential function. We can see the graph of the function here on the left. So the first thing that we need to understand is that e to the power of x, the function will be greater than 0 for every value of x. So you can see that here in the graph. It never drops below 0. And because it's usually used to model quantities, we're not going to have negative quantities. Therefore, this graph is never going to be negative. Either side of the axis, it will never drop below the x-axis. We will never have negative outputs. As x approaches infinity, the exponential e to the power of x approaches infinity very fast. So this is by saying as the input grows, the output grows even faster. And you can see that from the graph. As we go from left to right, the graph is growing really, really fast here. So it's going up faster than it's going to the right. So that's what this property is saying. That as our x values grow, as our inputs get bigger here on the x-axis, the outputs get bigger even faster. And you can see as I zoom out, you can see how quickly this exponential function really starts to grow. Then the next property, as x approaches minus infinity, the exponential function approaches 0. It approaches 0, but it will always be greater than 0. It gets very close to 0, as you can see here. As you go through negative values of x, if we zoom in here, we can see that the exponential function itself gets close to 0, but it never ever actually touches 0. If I condense this down and zoom in a little bit further, you're going to see that. So as we go in here, if we zoom in and zoom in, you can see it gets close to 0, but never ever touches 0. All right, so that is an important concept as well. So as the power of the exponential becomes more and more negative, the exponential itself approaches 0. And the final property here, e to the power of 0 is 1. So if your input is 0, your output is 1. Anything to the power of 0 is 1. So therefore, e to the power of 0 is 1. So before we go any further with the exponential function, we're going to take a look at solving exponential equations. Being able to solve exponential equations is an important skill related to exponential functions. So we can see a lot of exponential equations here, and we just need to understand how to solve these. So let's start off with a straightforward example. We look at the very first one here. E to the power of x equals 10, and we want to solve for x. So we've got e to the power of x equals 10. So how am I going to solve this? Well, what we're going to do, we're trying to solve for a power. So we're going to use logs. And in this case, we're going to use the natural log. By the natural log, I mean log to the base e. That is our natural log, log to the base e. And the reason we will use this is because of our natural log rule. So if we take, for example, log to the base e of e to the power of x. Remembering our log rules, what is this going to be worth? Log to the base e of e to the power of x. So what I can do is I can use my log rules. I can bring this power down in front. So I can rewrite this as x times log to the base e of e. All right. Now, what about this log to the base e of e that we see here? Well, we know that the value of this is 1. Why is it 1? Because we're thinking e to the power of what number will give me e. So if you have log to the base e of e, that's 1. So we're really just with x times 1, which is simply x. So log to the base e of x is equals to this, x times log to the base e of e, which is equals to x times 1, which is x. So moral of the story, log to the base e of e to the power of x is simply equals to x. And that's an important idea that's going to help us solving these exponential equations. One other important idea, log to the base e is often written as ln. ln coming from the Latin for natural log. All right, so if you see ln, that means log to the base e. So if you see log to the base e of x, that's the same thing as the ln of x. Okay, so now that we've examined this, let's go back to our log equation, our exponential equation over here. So we've already seen that log to the base e of x is simply x. So we use that idea to help us solve for the power. So because it's an equation, we have to do the same thing to both sides. So I'm going to get log to the base e of both sides. Or in other words, I'm going to get the ln of both sides. So that's what I do. So I get the ln of e to the power of x is equals to the ln of 10. And we've already seen that ln of e to the power of x is simply x. Okay, so some people like to look at it as the ln and e cancel, but we know what's really going on in the background. We've visited that here on the right hand side. So my next line will simply be x is equals to the ln of 10. And then it's just a case of putting it into your calculator. And our answer, if we stick to 3 decimal places, is x is 2.303. So that was fairly straightforward. In order to solve the exponential equation, in order to solve for the power here, we just got the ln, the natural log of both sides, and that allowed us to solve for x. So let's have a look at another example here. E to the power of 3x is equals to 150. So we've already seen that in order to solve for the power, you're going to get the natural log of both sides. So the ln of e to the power of 3x equals the ln of 150. And we know that the ln of e to the power of 3x is simply 3x is equals to the ln of 150. So if 3x is equals to the natural log of 150, then x is equals to the natural log of 150 divided by 3. And then we just put that into our calculator. And we'll get x is 1.67. Okay, let's have a look at one more example. Let's say I have 4e to the power of 2x is equals to 32. So once again, we know in order to solve for the power, we're going to get the natural log of both sides. But we have to deal with this 4 first of all. In order for our log and our e to cancel here, we need to have the natural log of just e, not the natural log of 4e or the natural log of 5e. So what we want to do here is, first of all, we're going to divide both sides by 4. First of all, so dividing both sides by 4, we'll have e to the power of 2x is equals to 8. And now we can get the natural log of both sides. So the ln of e to the power of 2x is equals to the ln of 8. We know that the ln of e to the power of 2x is simply 2x is equals to the ln of 8. So therefore, x is equals to the ln of 8 divided by 2. And put that into your calculator, and we'll get x is 1.0397 if we go to 4 decimal places. So that is how we solve exponential equations. And as I've already said, solving exponential equations is an important skill in working with exponential functions.